Hey, welcome to tutorial 22. Here we'll continue with FM and get into the technical details a bit so that we have a more complete understanding of how it works and how to build an FM instrument that's useful for creating specific pitches, melodies, chords, etc., instead of just making random stuff. Let's start with some basic principles. FM synthesis creates additional frequency components in the output spectrum called sidebands that appear in pairs on either side of the carrier frequency. Where these sidebands appear depends on the frequency of the modulator, and the number of sidebands that are present depends on a factor called index of modulation, which is directly proportional to the amplitude of the modulator. Before we take a closer look at the numbers, here's a sound example with a carrier at 800 Hz and modulator at 200 Hz. Right now the modulator amplitude is 0. This means the index of modulation is also 0, and the modulator signal is completely removed from the equation, and all we get is a pure 800 Hz tone. If we use mouse Y to control modulator amplitude, then we can control the number of sideband pairs that appear in the spectrum. This brings us to rule number 1 of FM. As the amplitude of the modulator increases, the number of audible sidebands increases. In other words, we get a wider and more complex output spectrum. Now let's use mouse X to control modulator frequency, like we did in the previous video. As modulator frequency increases, you can see that the spacing between sidebands increases. In fact, this is rule number 2 of FM, and that is the interval at which sidebands appear is equal to the modulator frequency. So here, with the modulator fixed at 200 Hz, sidebands appear below this 800 Hz carrier at 600, 400, 200, and above the carrier at 1000, 1200, 1400, etc. If we increase the modulator to 300 Hz, now the sidebands appear below the carrier at 500, 200, and they also appear above at 1100, 1400, 1700, etc. So let's go back to the mouse X version for just a second. Look at the spectrum analyzer and notice that as modulator frequency increases, the lower sidebands look like they're about to cross into negative values, but instead they sort of bounce off 0 Hz and get reflected back into the positive domain. There are different ways to explain this behavior. One way to conceptualize it is that a negative frequency means we're asking an oscillator to produce its periodic shape in reverse. In the case of a sine wave, this produces a waveform which sounds indistinguishable from its positive frequency counterpart. The only difference is that the polarity of the waveform is inverted. If we modify our code so that the modulator is 350 Hz, here's our carrier at 800, subtract 350 to get a sideband at 450, subtract again for a sideband at 100, subtracting again gives us negative 250, so here's our sideband at positive 250, and we can even see the next sideband at 600, although it's very quiet and probably has a minimal effect on our perception, if anything. So, back to the matter at hand. We now know that modulator frequency determines sideband spacing, modulator amplitude determines the number of audible sidebands. But what about carrier frequency? Well, the carrier frequency simply determines the point of origin around which this cluster of sideband activity occurs. So let's use mouse X to sweep the carrier frequency up and down. And the carrier and sidebands all shift together, but the relative spacing of the partials remains the same. This looks a little bit more convincing if we change the analyzer scale from logarithmic to linear. Okay, we're making progress, but we're not quite there. We still can't play a tune. I want to point out something that you might have already noticed using this line of code that was featured in the previous video. And that is, if we sweep the modulator frequency more slowly and listen really carefully, you'll notice that there are these pockets where we get a very clear sense of pitch. Like here, for example, where the modulator is almost exactly 100 hertz. And there are several other spots where this happens, and you can try to find some yourself. For example, it happens again around 250 hertz. And it also happens up here at our upper limit of 2 kilohertz. So rule number 3 of FM, or I guess this is maybe more of a guideline, we tend to get a very clear sense of pitch when the carrier and modulator frequencies form a simple ratio, like 2 to 1, 3 to 1, 3 to 2, something like that. So here, if the modulator is 100 hertz, we have a carrier-modulator ratio of 5 to 1. The shape of the waveform completely stabilizes. It's sort of difficult to see on this particular analyzer, but we have sidebands at intervals of 100 hertz. So we have the carrier here at 500, and then 4, 3, 2, 100 below, 6, 7, 8, 900, etc. above. We perceive this harmonic spectrum as having a clear sense of pitch at a fundamental of 100 hertz. Likewise, with the modulator at 250, we have a 2 to 1 ratio, which again produces a stable waveform and a fundamental at 250 hertz, and harmonics at 500, 750, 1000, 1250. A modulator at 2000 gives us a 1 to 4 ratio. And in this particular case, the math shakes out in such a way that we only get odd-numbered harmonics, 1500, 2500, 3500, etc. You can experiment with ratios of your own and see what kinds of spectra are produced. I think we're actually ready to start building a synth-def that incorporates these principles. We haven't yet talked about the math behind index of modulation, but we'll deal with that along the way. So I'm going to paste in our synth-def from the previous tutorial and make a few changes. Now, what we'd like to be able to do is specify one frequency value as an input argument and always hear that frequency as the perceived pitch. So instead of declaring two frequency arguments, now we're just going to declare one called freq, and two values, let's call them M ratio and C ratio, that we can use to independently scale the frequencies of the two oscillators so that we can more easily specify an FM configuration in terms of a carrier-modulator ratio. Default settings now sound like this. And check this out. Our frequency argument is behaving like a nice, normal frequency argument. Which means, if we want, we can think about pitch in terms of MIDI note numbers instead of cycles per second. So now, let's see what happens if we increase the carrier multiplier incrementally by integers. In this case, the intervallic spacing of harmonics stays the same, which means the perceived fundamental doesn't really change, but we end up listening to a cluster of harmonics centered increasingly higher and higher on the overtone series. And non-integer values will tend to give us spectra that we perceive as being inharmonic, with no clear pitch center, usually has kind of a bell-like sound. If instead we increase the modulator multiplier by integers, the carrier stays put, but the spacing of the sidebands increases, so we get different combinations of specific overtones. And again, non-integer values tend to produce inharmonic spectra. You can modify both of these scaling factors at the same time. For example, here's a ratio of 2 to 3, 5 to 2. Okay, let's talk about index of modulation, which, as I mentioned, is directly proportional to modulator amplitude. So as one increases, so does the other. Index of modulation is expressed as the ratio of modulator amplitude to modulator frequency. The reason this value is useful is because it loosely corresponds to the number of audible sideband pairs in the spectrum. The rule of thumb I tend to go with is the number of audible sideband pairs in the spectrum is equal to index plus 1. But whether something is audible is pretty subjective. In our synth-def, we're going to declare an index argument. I'm going to set it to 1 by default. And now I'm going to do something that might look a little weird at first. We're not actually going to use mod amp anymore. Instead, we're going to set the modulator mul value to be exactly the same as its frequency. And if we stop here, then the index of modulation is always going to be 1 because modulator amplitude and modulator frequency are equal, so index is 1. That's how our index equation works. So to incorporate our index argument, now we just multiply modulator amplitude by index. So now, if the index is 0, we should expect to hear a pure sine wave at note number 66. And we do. And as we increase the index of modulation, we see more and more sidebands populate the output spectrum. There's one last thing I'd like to do to our synth-def, and that is add an envelope to control the index of modulation. An index envelope allows us to dynamically shape the sound spectrum over the course of a single note, which is going to tend to make our sounds a little bit more lively and interesting, and it can also be useful for modeling the dynamic spectra of some acoustic instruments. I'll add a new variable for the index envelope. This envelope will start at our base index value, move to the index scaled by some amount that we'll specify, and then back to the base index. I'm going to set the default index scale value at 5, kind of arbitrarily. For envelope segment durations, it's possible to have this envelope be completely independent from the amplitude envelope, but just for fun, because I think it's kind of a classic thing to do, I'm going to lock them together so that they always have the same attack and release time. I'm going to throw some curve values into the index envelope as well. And in fact, I'm actually going to use these same curve values for the amplitude envelope as well, just to sort of further lock these two envelopes together. Now, because these two envelopes are always going to have the same length, we don't need another done action 2 to free the synth whenever it's finished. That's already being handled by our first envelope. And then finally, replace this static index value with our new index envelope. Let's try it out. Let's make the release a little bit shorter. You can see and hear that at the peak amplitude of the sound, the spectrum is relatively broad, and then as the amplitude decays, the higher partials fade away more quickly. It's kind of a subtle effect right now, but if we increase the index envelope scaling factor, then the peak of our sound has even more partials. And if we fine-tune the release curve of the envelopes, now we've got like a slap bass synth kind of thing going on. We can make the index envelope go in the opposite direction too. To do that, we just start with a higher base index and scale it by a value between 0 and 1. And let's not forget, we can also play around with the carrier modulator ratio. For teaching purposes, I've tried to keep this synth-def relatively simple. But as you can hear, it still gives you access to a huge world of FM sounds just waiting to be explored. The last thing I want to do is point out that there is a UGen called PMOSC, which stands for Phase Modulation Oscillator. Now, hang on a sec. I thought we were talking about frequency modulation. What is this phase modulation business? Well, In a digital context, most oscillators, including sine-osc, are wavetable oscillators, which means they read values from a table instead of mathematically calculating them on the fly. So modulating the phase of one of these oscillators means we're asking a wavetable pointer to move more quickly and more slowly through its wavetable. And indirectly, this affects the frequency of the oscillator in the exact same way that we've been doing. So FM versus PM, different implementation, but essentially same results. Technically, there are some differences, but they only really come into play if you've got a more complicated modulation network with multiple modulators, multiple carriers. And in those cases, phase modulation is considered superior because it's a little more flexible and it avoids some problems that can pop up with an FM approach. But this is all kind of advanced stuff, and for most purposes, you should consider FM and PM to be virtually equivalent. Let's actually look at the source code for PM-OSC. In the language menu, select Look Up Implementations, the hotkey is Shift-Command-I, type PM-OSC, and double-click it from the list to bring up the source code. Note also that the source code is available using this link in the help document. And PM-OSC is a so-called pseudo-UGen. Basically a UGen that serves as a shorthand for a more complex combination of other UGens. This caret mark here indicates that the AR method of PM-OSC returns a sine-OSC with another sine-OSC controlling its phase. So our version, which is more of a direct FM implementation, looks like this, with a sine-OSC added to a base frequency value, carrier 500, modulator 4, index 10. A phase modulation version would look like this, where we don't manipulate the frequency directly, but instead use a sine-OSC as the phase input for the carrier oscillator. And with PM, the math works out in such a way that there's no need to have the modulator amplitude and frequency be mathematically related to each other. Instead, in PM, index of modulation is the modulator amplitude. And from here, PM-OSC is a convenience that accomplishes the same thing with less code. But there's something important I need to point out here, and that is, at the time of making this video, there's an oversight in the source code for PM-OSC. When using sine-OSC, phase values should not exceed positive or negative 8 pi, according to the sine-OSC help file. Otherwise, I think they get clipped within these boundaries. But in the source code for PM-OSC, there's nothing preventing you from specifying a super high value for PM index that will cause the modulator output to exceed these boundaries. Now, if index is less than or equal to 8 pi, as it is here, it's not a problem. But if we set it higher than 8 pi, it starts to sound kind of weird. The frequency of the carrier has this staircasing effect because the internal phase values have a range that's bigger than plus and minus 8 pi, and so those values are getting truncated. And we end up losing the smooth sinusoidal movement in the carrier frequency. It's supposed to sound like this. Now, of course, sound is sound, and if you're experimenting and you like this sound, go for it. But if it's classic FM synthesis you're after, then it's possible that PM-OSC won't deliver the correct results. Fortunately, SuperCollider is open source, so we can fix it ourselves. And in fact, it's really, really easy. All we need to do is use mod 2 pi on the phase values to wrap them within appropriate boundaries. Probably mod 8 pi would also work, but it says 2 pi here, so that's what we're going to do. So watch this. We go into the source code file. We add .mod 2 pi to the end of the modulating oscillator. Let's be consistent and also fix the KR method while we're here. Save this source file, and then in the language menu, recompile the class library, or just hit Shift-Command-L. This has the side effect of quitting the audio server, so we need to reboot it. And now, PM-OSC works perfectly. I noticed this issue in the process of making this tutorial and opened an issue on GitHub, so this might be fixed in a future release. But regardless, once it's working properly, PM-OSC is a handy tool if you want to do straight up classic FM stuff with one modulator, one carrier, both sine waves. And as we've seen, even this super basic construction is capable of a huge variety. And if you want, you can just as easily build a synth-def using PMOSC instead of explicitly making your own carrier and modulator, as we did here. But personally, I prefer this DIY approach because you can add your own spice and variation however you like. For example, the carrier and modulator don't have to be sine waves, they can be any type of oscillator you like. Or maybe you want independent envelopes for amplitude and modulation index, so they're not always locked together. Whatever you want, it's all doable. And maybe coolest of all, you can design your synth-def to have multiple modulators and or multiple carriers that are affecting each other in series or parallel or being summed together or whatever, and just see what kind of sound comes out. Just to get the wheels turning a little bit, here's an example. Let's give ourselves a second modulator, modulating the first modulator, and then that signal modulates the carrier. And the sky's the limit. It can get just about as crazy as you want, so don't feel like you need to stop there. Anyway, that's it for tutorial 22. I hope this video provides a more complete understanding of the concepts behind FM, and I hope it gives you lots of ideas for experimenting, creating interesting FM sounds and sequences, and whatever else you want to do. If you cook up something cool, I'd love to hear it, so feel free to link it in a comment. And I'll also try to put a link in the description to some of the FM examples that I was developing in the process of making this video. My example code got kind of long and a little complicated, so I figured I'd make it available if you want to study it or mess around with it, but not actually put it in the video and take up time. In the next tutorial, we'll take a look at wave shaping and wavetable synthesis in SuperCollider and some of the things you can do with it. Should be a lot of fun. So, as always, thanks for watching. See you next time.